Hi, I'm Jonathan, and I'm going to be talking about the paper Interactive Proofs for Verifying Machine Learning. This is a joint work with Shafi Goldwasser, Guy Rothblum, and Amir Yehudayoff. And the question we considered was, when is verifying cheaper than learning? What I mean by this is the following. So we're all familiar with the idea that sometimes solving a certain problem can be harder than verifying a solution provided by someone else. And that's, of course, a central theme in computational complexity, the P versus NP problem, and so on. But what about supervised machine learning? Are there supervised machine learning problems where finding a good hypothesis is hard, but verifying a hypothesis provided by someone else is easy? So that's the question we considered. And of course, we're interested in knowing, are there cases like that? When is it easier to verify than it is to learn? How much easier it is, and so on. The setting we used is the following setting. So there's some unknown distribution that provides samples of the form x and y, where x is some instance and y is the label for that instance. And there's a verifier which has the objective of finding some hypothesis that is good at predicting the labels, predicting y given x. The verifier can take random samples from the distribution, but it doesn't want to do all the hard work of finding that hypothesis itself. Instead, it's going to use the help of another party, which we call the learner, the prover. And that party maybe has a lot more computational resources or stuff like that. And the verifier wants to use the help of the prover in order to find a good hypothesis. So the prover can also take samples from the unknown distribution, and the verifier and the prover can exchange messages. And at the end of the interaction, after they finish sending messages to each other, the verifier will either reject the interaction or it will accept the interaction and output some hypothesis. So, for example, maybe the prover will take samples from the distribution and run some machine learning algorithm, find a good hypothesis using those samples, and send that hypothesis as a message to the verifier. Then the verifier takes additional samples of its own from the distribution and uses them in order to decide whether this hypothesis is good or not good. And after it does that, it either outputs the hypothesis if it thinks it's good, or it rejects. So that's generally the type of interactive proof we're considering in this paper. And we're asking, when is the work that the verifier does cheaper than just learning the hypothesis itself without using the help of some external prover? And when I say cheaper, I mean both quantitatively. So for instance, maybe the verifier needs less samples in order to do the verification than it would if it was just doing learning by itself. So this is number of samples, runtime, etc. Or it could be qualitatively cheaper. For instance, maybe the verifier uses some sort of cheaper access to the distribution. So for instance, maybe the verifier has random sample access to a distribution that provides samples of the form x and f of x, while the prover has query access to that labeling function f, which is a stronger and more expensive type of access. So then the verifier would gain the benefit of finding a good hypothesis without needing to have that more expensive kind of access itself. So that's generally our setting. And let's do an example of when this kind of setting might be useful. So imagine some sort of commercial situation where you have one company, V, the verifier, and they have some machine learning tasks that they want to solve. But instead of solving it themselves, they outsource their machine learning work to some prover, P, which is a machine learning services provider. And what the provider supposedly does is what it's supposed to do is to collect a lot of high quality data related to this particular machine learning problem, and train a good machine learning model for that data, maybe using a lot of compute power, maybe some deep neural networks, whatever. And then it will send that hypothesis to the verifier, back to the company that ordered it. And now the verifier receives the model, and it sees that the model has accuracy 80%. It can predict, the correct label Y with 80% probability. And like verifying that it's about 80% is easy. Just, take 100 samples or something like that and see what percent of those samples are labeled correctly by the model. And that's a pretty good estimate of the correct true accuracy of the model. But if V knows that the accuracy is 80%, it's still not clear if V should accept or not. Is 80% good enough, not good enough? Maybe the provider was slacking off and they could have gotten to 90% if they would have done more work. So in order to define this a bit more formally, we followed the definition of probably approximately correct, pack learning, which is a very common definition in learning theory. And the way this definition works is we have some class H of functions, x, functions from the domain x to 0, 1. And there's some loss function that for each hypothesis H in the class, little h in the class big H, tells us how good or bad little h performs. So for instance, this particular loss function here, which is what we'll mostly work with, is the 0, 1 loss. It says, what is the probability that H classifies X incorrectly, predicts the wrong label? And then there's this number here, opt, which is the best possible loss you can achieve if you're using hypotheses from the class H. So this is the minimal loss you can achieve if you're using hypotheses from H. And we say that a class big H is pack learnable if there exists an algorithm such that for every epsilon and delta and every unknown distribution, if we execute this algorithm with samples from the distribution, then with high probability, the result is approximately correct. It's probably approximately correct. So with probability at least 1 minus delta, the loss of H, the output is at most epsilon worse than the optimum loss. So kind of inspired by this definition of pack learning, we introduced the following definition that we call pack verification. And it goes as following. We say that a class of functions H is pack verifiable if there exist two algorithms, a verifier and a prover, such that for every epsilon and delta, for every unknown distribution D, the verifier and the prover satisfy completeness and soundness. Completeness means that if I run the verifier and the prover so that they interact with each other, and they have sample access to the distribution and so on, then with high probability at least 1 minus delta, the verifier will not reject the interaction, and it will output a hypothesis H that is approximately approximately correct. So it has loss at most opt plus epsilon. That's completeness. Soundness means that for any prover, maybe a different, dishonest, malicious, and possibly computationally unbounded prover, so for any prover, if that prover interacts with the verifier, and they both have access to the distribution and so on, then this malicious prover cannot cause the verifier to output a hypothesis that is not approximately correct, except maybe with some small probability. So the verifier will either reject the interaction or it will output a good hypothesis, or with very, very small probability, it will output a bad hypothesis. So that's soundness. And we're particularly interested in cases that satisfy double efficiency. So what we mean by that is that both the verifier and the prover need to be, the honest prover need to be efficient. So the dishonest malicious prover might be computationally unbounded, but we want both the verifier and the honest prover to be efficient. And the motivation for that is that we want, for instance, like we saw in the commercial setting, we want some, actual real party to be able to instantiate the prover and run that algorithm and so on. So in order to allow, the machine learning provider to execute the prover, we want the prover to be efficient. So that's our definition of pack verification. And the first thing to observe about our definition of pack verification is that in the realizable case, when we assume that opt is 0, then verification is easy. So if we are promised that there exists some hypothesis in the class that has 0 loss, then pack verification is easy. And why is that? So generally, if what the verifier does is it can take order 1/epsilon random samples, and it will accept the hypothesis that the prover provides if and only if that hypothesis classifies all the instances in the sample correctly. And so if the prover was honest and it sent a hypothesis that had 0 loss, then the verifier will always accept. And in fact, even if the prover sent a hypothesis that it has, only very close to 0, slightly more than 0, but close to 0 loss, then still the verifier will accept with high probability. However, if the prover sends a hypothesis that has a loss that is too great, bigger than epsilon, then the verifier will reject with constant probability. So what we see is basically a separation here between learning and verification. So in the realizable case, it's possible to do verification using order 1/epsilon samples. However, we know from learning theory that in order to do pack learning in the realizable case, we need order d/epsilon samples, where d is the VC dimension of the hypothesis class, capital H. And this VC dimension is unbounded. It could be an integer as large as we like. And so this basically means that the gap between learning and verifying can be unbounded, at least in the realizable case. So that's a nice, encouraging result that shows that maybe we could get nice separation results like this, but it's not very surprising for the realizable case. Things become a bit more interesting in the agnostic case. So in the agnostic case, we're not making any assumptions about opt, the best loss that we can achieve using our class. And so basically what the verifier needs to do is it needs to verify that this inequality holds for the hypothesis H that is proposed by the prover. And as we sort of already discussed, estimating the left-hand side here, the loss of the particular hypothesis, is easy. Just take 100 samples and see what percentage of them are labeled correctly by this hypothesis, and that's a very good estimate. The problem is that the verifier doesn't know what opt is. And so this is where the prover comes in. The prover will, let's say, send the hypothesis to the verifier, and then it will interact in an interactive proof with the verifier in order to convince the verifier that opt is large. It's large enough to make this inequality hold. So that's basically what the prover needs to do. It needs to be able to prove that opt is large. And now let's see an example where this is actually possible in the agnostic case. So This is a very simple example, and the main point is that we are able to get a separation between the sample complexity of learning and verification, also in the agnostic case. So the class of hypothesis that we're using is this class of monotone increasing Boolean threshold. So it's just like threshold functions like this that start off as being 0, 0, 0, and then at some point they jump up and continue to be 1, 1, 1 from there on. So this is our class of hypothesis. And the prover sends some particular hypothesis, and it wants to convince us that that's a good hypothesis, and therefore it needs to show that opt is large. So let's assume that opt equals the loss of ft for some threshold function t that we don't know what it is. The verifier doesn't know what it is, but we can assume that there exists some threshold like that achieves the minimal loss. How will the prover convince the verifier that opt is large? So we call this a certificate of large loss for thresholds. And the way this works is the following. The prover will send two sets, A and B, such that A is some subset of the domain 0, 1 times 1, and B is some subset of the domain times 0. And A and B are both intervals. So we can think of A as having a start point and an end point. So within some interval within the 0, 1 interval. And it's a set of points that are all labeled as 1. And again, B is also an interval, set of points that are all labeled as 0. Formally, A and B are both events within the probability space where the unknown distribution is defined. So P sends these two events, A and B. And in addition, they satisfy this requirement that A is to the left of B. So all the points in A in this interval are smaller than all the points in the interval B. And why is this a good idea? So what the verifier can do when it receives these two events is it can estimate the weight of each of them. So, you know, the verifier can take 100 samples and see how many of them fall inside the event A. That's a good estimate for the weight of A, and then do the same thing in order to estimate the weight of B. And it turns out that opt is at least the minimum of these two quantities, these two probabilities, the probability of A and the probability of B. Why is that? So it's quite simple. Basically, if we have some threshold function and it labels even one point in A correctly, and that means that we have this threshold function and it goes up and labels a point in A correctly. So from that point onwards, everything to the right of that point needs to be also labeled as 1, because everything is A in A is labeled as 1. So from this point and to the right, everything is labeled 1. In particular, that means that all the points in B are classified incorrectly by this threshold. So if a threshold classifies any point in A correctly, that means it classifies all the points in B incorrectly. And vice versa, if it classifies even one point in B correctly, that means it remained at 0 up until that point at least. And so it classified all the points in A as 0, which is incorrect. That means that you can't have a threshold that will classify both A and B correctly, and therefore the loss of the threshold is the probability of the event of misclassifying a point is greater than the loss of at least A or B, the minimum between the two. So what we get this way is basically an interactive proof where the prover sends these sets A and B, and it satisfies soundness and completeness. So if there exists, the soundness says that if there exists a certificate A and B such that the weight of the minimum between weight in A and weight of B equals L, then opt is at least L, exactly for the reason I just stated, which is if you classify one point in A correctly, you classify all points in B incorrectly. Then completeness says is that if opt equals L, if the best loss you can achieve is L, then there exists some certificate that shows that, or actually shows something related to that, which is there exists a certificate A and B such that the minimum weight between A and B is at least L over 2. So it's not very hard to prove both of these claims. And using this, we can, using this idea, we can prove the following result, which is our first result in the paper. And it says the following. It says there exists some sequence of classes, H1, H2, H3, and so on, such that pack learning the class HD requires at least order D random samples. On the other hand, pack verifying the class HD is possible using order square root of D random samples. And furthermore, both the prover and the verifier or efficient, they run in time polynomial and the number of samples and so on. So this is basically a quantitative separation between learning and verifying. And the idea of the proof is basically to take the certificates of large loss for thresholds and generalize that idea for a class that has VC dimension D and not a constant VC dimension like the threshold had, but this will be a D threshold that has VC dimension D. And then the certificate will be a set of 2D events instead of just 2 events. And the verifier will now need to verify that all these events satisfy some condition that shows that opt is large. And it turns out that using ideas from distribution testing, you can actually do that using square root D samples. So that's the idea of our first result, quantitative separation between learning and verifying. Our second result is kind of the opposite. It says in some cases, learning and verifying or require the same amount of random samples. They cost the same. So formally, there exists a sequence of classes, H1, H2, H3, and so on, such that pack learning the class HD is possible using order D random samples, while pack verifying the class HD requires order D random samples. And so you don't get any saving by doing pack verification for this class. And the proof of this is basically from the probabilistic method. If you choose the class according to some clever distribution, then you will get this result. So I have some caveats. In particular, so even though pack learning this class is possible using order D random samples, the runtime of the algorithm that does the pack learning might not be polynomial. It might be exponential in the number of samples. So the runtime is not actually efficient. And on the other hand, the verifier, the lower bound in verifying only applies to proper verification. And what I mean by that is that it only applies to interactive proofs where the verifier outputs a hypothesis that belongs to the class HD. Maybe possibly if you allow the verifier to output a hypothesis that has a low loss but does not belong to the class HD, then this lower bound wouldn't hold. But that's the overview of our second result. And basically what we've seen so far is that from a quantitative point of view, there are some cases where learning is more expensive than verification. Verification is cheaper. And in other cases, that's not true. In other cases, they're both equally expensive. And so it would be very interesting to understand when exactly this happens. When is learning uh, more expensive than verification, and when it is not. When can you save using verification, and when can you not save in sample complexity, let's say. Um, our third result um, is a qualitative separation. So this result talks about the class H of t-splice Boolean functions from the Boolean hypercube to 0, 1, and I'll define that class in the next slide. But the point is sort of that if you adopt the learning parity with noise assumption, which is a very common assumption in cryptography, then agnostic learning the class H from random samples is computationally hard. Like in fact, even learning just a single parity is hard, and H is somehow linear combinations of parities, so that's even harder. So if the LPN assumption is true, then it is not possible to efficiently agnostically pack-learn the class H. However, what we prove is that H is pack verifiable using an interactive proof system with the following properties. So the verifier V uses only random samples from the distribution. The prover has query access to the labeling function. So if the distribution is a distribution over samples of x and f of x, then the prover can just query that labeling function f on any x that it chooses. And both the verifier and the prover are efficient. They run in time polynomial in the parameters of the problem, and the verifier uses, they both use samples or queries polynomial in the parameters of the problem and so on. So basically, this result is saying you cannot efficiently pack learn this class using random samples, but you can efficiently pack verify this class using random samples. That's the idea. And I'm going to spend the rest of the talk explaining a bit about this result, and then I'll wrap up. So first of all, as promised, let's define this class of t-splice functions. So for any s, which is a subset of the numbers between 1 and n, we define a chi of s to be a function from the Boolean hypercube, in other words, a vector of n bits, to plus minus 1. And this is basically a parity of the subset of the bits that correspond to this s. The subset s of the bits takes a parity, that's chi of s. And Fourier analysis tells us that any function f can be written as a linear combination of these chi s's. We call the chi s's characters, and this thing here, the f hat of s, is the Fourier coefficient of s that corresponds to this particular chi of s. So any function Boolean, any function from the hypercube to the reals can be written as a linear combination of characters. And the class of t-splice functions is simply those functions where the most t non-zero coefficients. So functions, each of which is a linear combination of at most t characters. And the idea for getting this qualitative separation is to use two well-known algorithms, the Cauchy-Lewitz-Mansour algorithm and the Goldwasser-Levin algorithm, and combine them in a certain way that allows the verifier to leverage the help of the prover. So let's start with a refresher about what the Cauchy-Lewitz-Mansour algorithm is. So this is an algorithm that learns the class of twosplice functions using random samples. However, under the assumption that the target function f, the function we want to identify, um, the algorithm knows in advance what is the set of non-zero coefficients, non-zero Fourier coefficients. And so basically what the algorithm needs to do is just figure out what is the value of those non-zero coefficients, but it already knows in advance which coefficients those are. And this is actually fairly simple to explain. So I'll explain how the Cauchy-Levy-Mansour algorithm works. So what happens is that the Fourier coefficient of f is basically the projection of f, the function f on the character, or the inner product between them, and inner product in this context is defined to be expectation. And so the Fourier coefficient s that we want to estimate is actually defined to be an expectation of some random variable, which is the product of f and chi of s. And because this product is just a random variable, which is bounded, then again, if we take 100 samples and we take the average of the f of x times chi s of x for those 100 samples, then that would be a very good estimate of the two expectations from Hofstadter's inequality. So basically, we can estimate each one of the required Fourier coefficients in this manner, and then that's it. You now have the good estimates of all the Fourier coefficients, and it turns out that the function that you get that way is very close to the correct function. If you take the function with all the estimated coefficients, then that's a good estimate of the function f. And in fact, it turns out that you don't even need to estimate all the Fourier coefficients that are non-zero. It's enough to estimate the heavy ones, those that are have absolute value at least tau for some tau that depends on how good of an estimate you want of the function f. Okay, so that's the Cauchy-Levy-Mansour algorithm. The second algorithm is the Goldwasser-Levin algorithm. The Goldwasser-Levin algorithm is basically complements the Cauchy-Levy-Mansour algorithm because it confines this set of heavy coefficients of f. So if you tell it, I want to find all the coefficients that weigh at least tau, that's what the Goldwasser-Levin algorithm does. However, the Goldwasser-Levin algorithm requires query access to f. Okay, so using these two building blocks, Cauchy-Levy-Mansour that can learn the function if you know the heavy coefficients and requires only random samples, and the Goldwasser-Levin algorithm which can find the heavy coefficients but requires query access, we can put both of these together and get an interactive proof for pack verifying the class of T-splice Boolean functions. And the idea is, okay, so we use the Goldwasser-Levin algorithm to find the set of heavy coefficients. And then once we know that set of heavy coefficients, we use the Cauchy-Levy-Mansour algorithm in order to learn the function f. The problem is that, as I stated, the Goldwasser-Levin algorithm requires query access. And so, for instance, the verifier can't run both of these steps. It can't run the first step here in this, among the two steps, the verifier cannot run the first step because it doesn't have query access. And so what we propose is the following solution. The verifier is basically going to simulate the Goldwasser-Levin algorithm. And in this simulation, it executes the Goldwasser-Levin algorithm, and then it knows, okay, in order to complete the algorithm, I'm going to need to query f at these particular points, f of x1, x2, and so on. What it does at that point, it can't query f because it doesn't have query access. It's going to take some additional random samples, x tilde 1, x tilde 2, and so on from the distribution, because it does have random sample access. And each of these random samples comes with the correct label, f of x tilde 1, and so on. And then what the verifier does is it's going to delegate the queries that it needs to the prover. So it's going to send x1 until xm to the prover and tell the prover, please use your query access and tell me what f of x1 is, what f of x2 is, and so on. However, in addition, it's going to send these x tilde 1 and x tilde 2 and so on, which it already knows the correct label for. And it's going to send both the queries and the x's from the sample mixed together to the prover so that the prover can't know which subset of these x's the verifier knows the correct label for and which subset it does not. And what that means is that if the prover is honest, then what it will do is it will actually go and query all these x's, both the regular x's and the x tilde ones, and send those results, the correct values, to the verifier. The verifier will continue the simulation of the Goldwasser algorithm, and then it finds f of t, the heavy, it finds a set of heavy coefficients that weigh at most tau, at least tau. And from that point, it can proceed on its own because the Kuchelewicz-Mansour algorithm only requires random samples. However, if the prover was not honest, then that means that how is it not honest? It sends some answers that are not correct. So instead of sending f of x, it sends some other value for some of these x's. But in that case, the verifier will detect that the prover is dishonest with high probability, because with high probability, if we choose, the number of x tildes correctly, then with high probability, if you're dishonest enough, then you're going to hit some of these x tildes. You're going to provide incorrect answers for some of these x tildes. And then the verifier who knows the correct answer will know that the prover is cheating and will know it needs to reject the interaction. So that's basically the idea of this qualitative separation. In order to show that this actually works, you need to kind of dig deeper into the details of how the Goldwasser algorithm works, and you need to show that you can in fact somehow hide a set of x tildes within the set of actual queries in a way that the prover won't be able to distinguish which are the actual queries that the verifier wants to know and which ones are the decoys that are just planted there in order to catch it. So that requires some additional details. We will be posting a additional video probably in the comments to this video that explains the details of that slightly more full, in more full detail. But this is the basic idea of how it works. So to summarize, what we've seen so far is the definition of pack verification and some motivation. For instance, maybe if you want to have a business that machine learning as a service or something, you outsource machine learning, then it might be useful to be able to have a path verification interactive proof. Then we discussed quantitative separations between learning and verification. We saw that for some classes, verification is cheaper, requires less samples, and actually it also requires less runtime in that particular example. The example of the threshold functions, or the d-threshold functions, you have a situation where the verifier is cheaper both in samples and in runtime. And we saw in other cases, for instance, if you just basically choose a random class of hypothesis, that verification and learning require the same amount of samples. And Additionally, qualitatively, we we saw that it's possible to learn the class of Fourier splice Boolean functions using random samples only. So it's possible to verify that class using random samples only, even though learning that class is probably not possible using random samples only, according to the learning parity with noise assumption. And actually, this class of T-splice Boolean functions is a fairly important class. It contains shallow decision trees and AC0 circuits and DNF formulas with small clauses. So this is actually an interesting example, I think. And there are still a lot of interesting directions for future work. So first of all, it would be, I think, very interesting to characterize exactly when there is a gap in sample complexity between learning and verifying and how big that gap is. If you think about learning, so in learning you have the VC dimension, which kind of completely characterizes when pack learning is possible and how much samples that would require when it is possible. So developing something similar for pack verification, I think that would be a very interesting direction, and we've already made in subsequent work we've already made some progress in that direction and some small progress. Another direction is to show efficient pack verification interactive proofs for some real-world hypothesis classes. So for instance, if you're thinking about delegation of machine learning, can you do pack verification for some actual real-world classes that people use in real-world machine learning settings, like random forest, neural networks, SVMs, and so on. Another direction is to develop pack verification protocols for replication of scientific publications. So this is another motivation that might be interesting for pack verification, which is, let's say someone publishes a paper where they did an experiment and they say, here, this is our experiment, and these are our results, the conclusions from the experiment, and so on. So traditionally, what you would do would you'd go and replicate that paper. You'd go and repeat basically the whole experiment independently in some other lab and see if you get the same results. But maybe instead of just publishing the results originally, you could somehow publish a prover for the results. And that would allow people to, instead of replicating the whole experiment, they could just replicate a smaller experiment, basically create less samples in the replication, and then using a verifier, they can interact with the prover and basically prove that with high probability the result in the original paper was correct, even though the replication didn't actually, do as many measurements, create as many samples, and so on. So that, I think, is an interesting direction. Another thing that would be interesting to look at is to consider the power of interaction. So if we allow more rounds of messages being exchanged between the prover and the verifier, does that make pack verification easier or not? How is the power of pack verification related to the number of rounds in the interactive proof? Another thing that would be interesting is to consider verification of other kinds of data analysis besides supervised machine learning. So you could think about dimensionality reduction or clustering or all sorts of other tasks that are not supervised machine learning, and see if you could do verification for those tasks as well. And another thing you could do is you could consider other guarantees besides the PAC guarantee. So in PAC, what we're basically verifying is that with high probability, the hypothesis has low loss or high accuracy. But that's just one property that the hypothesis can have with respect to the unknown distribution. There could be other properties that we want, good properties that we want the hypothesis to have with respect to the unknown distribution. For instance, maybe we want the hypothesis to, be algorithmically fair in some sense, or we want it to be safe. It's a self-driving car, and we want it to, some guarantees that it is safe. So those are different kinds of properties that the hypothesis can have with respect to the unknown distribution. And one could imagine developing verification interactive proofs for those properties and not for the accuracy, or in addition to the accuracy. Okay, so that pretty much wraps up my talk. Thank you very much for watching, and we'll be hanging out on the Slack channel, and we'll be very happy to answer any questions you might have. Thank you.